How big do you think this room is?
Good morning. Welcome to CES. Welcome to NVIDIA Live. Setting the stage, we are live at the Fontainebleau Theater here in Las Vegas. In just about an hour, Jensen will take the stage to share NVIDIA's vision of where AI is headed. And this panel has the daunting task of warming up this really smart audience before the most legendary keynote speaker takes off. What we will do is first start with introductions, and then we will have a panel of industry experts to talk us through a wide range of topics within the AI ecosystem. So starting with myself, I'm Vivek Arya. I'm a semiconductor analyst at Bank of America Securities, and I'm joined by...
I'm Sarah Guo. I'm the founder of AI-native venture firm Conviction.
And my name is Mark Lipacis, a senior semiconductor analyst from Evercore ISI.
Great. Thank you, Mark. So in this first session, we will talk about AI infrastructure, where we are coming from, where we are headed, and we are joined by Sridhar Ramaswamy, who is the CEO of Snowflake. Before I bring in Sridhar, let me just kind of walk you through a memory lane. AI is not the first large deployment in technology infrastructure. We have had the build-out of the internet, the rollout of fiber optic capacity throughout the globe. We have had the rise of cloud computing. We have had a big infrastructure cycle in 3G, in 4G, in 5G. Before I joined Merrill Lynch, I used to work in industry, and I have often lived through the boom and bust of some of those cycles. So that's why it's fun for us to contrast what we are seeing now versus what we have seen before. And you know, it's always risky to say it's different this time, but it is different this time for the reason that in the last 3 years, almost $800+ billion has been spent on AI infrastructure. And if I look at our forecast, close to $600 billion will be spent on AI infrastructure in 2026, right? So that's a lot of funding. You know, the question of where is this money going? What is the return on investment? You know, this B word, the bubble word, comes up a lot. In fact, I was reading Bloomberg yesterday, and they mentioned that just in the month of November, there were 12,000 articles with the word bubble right in them. So in my view, we actually have a bubble in the media headlines that talk about you know, where AI has been going. From my perspective, there are three things that make this infrastructural cycle different. Number one is the fact that there has been seamless adoption. Number two is high utilization. And number three is the amount of funding and the amount of very well-financed capital that is going into this infrastructure. So if we go through these three topics quickly, first of all, seamless adoption. The day ChatGPT was launched in November 22, every person with a PC or a mobile device, and that's close to 5 billion plus users, were able to access that service immediately, right? It was seamless. Unlike some of the prior cycles, you know, the build out of the original internet, where yes, a lot of fiber optics was deployed, but the end users were not ready. And that is partly why, you know, that build out stopped in early stages. There was a lot of capacity deployed in the core, but the usage, right, only happened over a much longer period of time. So number one is seamless adoption. Number two is the fact that we are seeing very high utilization of this infrastructure, right? You know, back when I was working in industry, we would talk about the amount of fiber that was being deployed, and then there was a new interesting term that came up, dark fiber, right, which is kind of an oxymoron, because the reason you put fiber is because you want to light it up. So there was all this dark and underused fiber that was in the ground, but what you don't hear is dark compute, right? What you see is all the compute infrastructure that is being deployed is being utilized very effectively, right? Even, you know, 6-7-year-old GPUs are being fully utilized, other custom chips are being fully utilized. So that, I think, is another very, very important difference. And to us, if there is one metric that people should watch for, is the utilization of this infrastructure. I think that's far more meaningful metric to measure the success of this build-out. And then the third and final aspect is that unlike the prior cycles, you know, there were a lot of companies that were, let's say, not as well funded. Right, this time the funding is being done by companies who are generating exceptional amount of free cash flow. If you look at the amount of capex that has gone into the ground, that's only 2/3 of the cash flow of operations from these companies. We think their free cash flow continues to stay positive, but that's another thing to watch out for as another leading indicator to see the success of this cycle. So we think this is the creation of brand new infrastructure. So that's the state of the union, but let's talk about where we are going. And for that, I'm really delighted to bring in Sridhar Ramaswamy from CEO of Snowflake. So maybe Sridhar, let's talk to us about the collaboration you have with NVIDIA. How did that come about? What are you doing? And what are the emerging use cases that you see in the enterprise?
Thank you, Vivek. I live entirely in the software space, so I'm a natural complement to some of the folks that we have on the panel here. And back to your point about high utilization, I think what's very unique about this moment is the many different places where AI is creating value. Even with the old chips, for example, we built a search engine, this was 3-4 years ago, entirely on A10s, which were already not even the top leading models in the world. And so we see a lot of our customers run very large data processing jobs, for example, on small models running on previous generations of infrastructure, they get utilized. On the other hand, at the very top, foundation models that are leading ones are doing exceptionally well because of their applicability in areas like coding agents, where they are unleashing an enormous amount of productivity. And now you're talking about people that are making easy $200,000-$300,000 every year. And so they're not going to hesitate about spending on a SaaS service that's going to make them more efficient. I think that's why AI is pretty unique in terms of how much value that it's creating. We have launched a bunch of data agents on top of Snowflake. In fact, I have one running right on I access it on my phone. And anytime I want information about a customer, I just turn to it and go, how are we doing with this particular customer? Do we have a relationship? Is it up? Is it down? That kind of access is something that every CEO wants to get to the latest information about how their company is doing. And I think these are the many reasons why you're seeing such excitement in this space. Our relationship with NVIDIA goes back many years. Jensen has actually been an honored guest in 2, I think, of our last 3 Snowflake summits. We collaborated with them very deeply. Obviously, all of our AI products, including Snowflake Intelligence, run on top of NVIDIA chips. We used to train pretty large foundation models once upon a time. We don't quite do that anymore. Those were done on NVIDIA chips as well. We also collaborate with them in the nitty-gritty detail. What are the right embedding models that are going to make search products work much more effectively? And I think the big prize that we are both after is in the future when GPUs can be applied not just to specialized inference on top of foundation models, but also to things like data computation, which is what we specialize in. So I think we're very much in the early innings of how are GPUs, how is accelerated computing going to impact a lot of things that Snowflake does.
Right. No, I think I'm glad you brought those points up, and I think that kind of ties to the intro that what we are seeing is kind of very strong, seamless adoption, and this is being used in kind of mission-critical infrastructure. This is not, build it and they will come. But when I'm sure there are certain obstacles, right? That there are certain enterprises who are still kind of resistant to the adoption of AI. Mm-hmm. What do you hear from them, Sridhar, and what do you think it'll take to get them over the hump of adopting this new tool?
Look, practical problems are always going to be there. Anytime you have a new computing paradigm, data is going to be sent over to a new class of chips. All reasonable customers, your employer included, have a lot of questions about, hey, what's happening with this data?
Right.
Who owns this data? For example, at Snowflake, the simplest answer that I give every customer is your data is your data. We process it on your behalf. We do nothing else with it. There are questions like that. Part of what people are very finicky with data is data sovereignty. They don't like it when data moves from one location to the other. In a consumer service, ChatGPT can get away with not really telling you where your request is going to be handled. Right. It can be in the US, it can be in Europe, it can be in Japan. It doesn't matter to you as a consumer, but as an enterprise, that's not the viewpoint that you take. You care a lot about where's the data resident, how does sovereignty come in. we often end up dealing with things like micro shortages. Back to your point about full GPU utilization, where we have customers in Germany that don't quite have capacity right in Germany, and we have to go negotiate with them about is it okay to send that traffic to Sweden or not.
Right.
So there are these kinds of practical problems that are going to come up, and driving change through an organization. When it comes to day-to-day, how are jobs going to get done? Can you convince people to do them differently? There's no easy answer to that. We have a great sales agent on top of our own data, built on top of Snowflake, but it's an entirely different story for me to tell each and every one of my sellers, you need to be demoing this on your phone every single day. That's a new muscle. They have to learn it. And as leaders, we have to come up with a whole set of techniques for how do we drive usage in a positive way within every organization. That kind of social change is just hard. It takes time.
Right.
In this transition, we have the inbuilt distribution of everybody having a smartphone, a laptop. And so you have this massive prosumer adoption that's really happened. And I think that the enterprise businesses who know how to do change management with these large organizations are really going to benefit this next year from consumers and prosumers having experienced the power of AI for themselves. And so I think Snowflake and NVIDIA and companies that, have those relationships with customers are really well suited for that for this next year.
That's right. And we very much think about things like agentic technologies as natural extensions of what we did as a data platform. Why do people bring data to Snowflake? It's because it's easier to manage, easier to get it AI ready, easier to get value from it. And an agentic platform fits right on top of that. I basically tell our CIO or CEO that we deal with, we can put that information in your fingertips. It's an easy sell.
Right. Got it. The one other thing I find very fascinating about this rollout is how it's suddenly becoming more global in nature also, right? It's like you follow where power is being deployed. That's where AI is being deployed. And we are seeing infrastructure come up in the Middle East. We are seeing infrastructure come up in Asia. How is that changing, Sridhar, your kind of go-to-market? If there is more and more computing that is available right across the globe, how does that change your strategy?
So Snowflake runs on top of the hyperscalers. And we have benefited from effectively infinite compute capacity when it came to regular computing. That's what has defined Snowflake's success, because we often rent CPUs on demand. We don't have to make pre-commitments. And so that model actually has carried over on the GPU side. I don't worry, for example, as much about bubbles, because we are not making large commitments. We are not buying hardware. We are not setting up data centers. Neither are our customers. You don't need to make pre-commits in order to use AI and Snowflake, in order to use Snowflake intelligence. It's actually very, very beneficial for there to be large deployments everywhere, because as I said, data sovereignty is very much an issue. In the geopolitical environment that we live in, a customer in Germany wants no part of that data going over to some other continent, let alone or anything else. So I think from that perspective, this build out is very, very helpful, that it is more and more decentralized, and demand for that is going to keep going up.
And how do you see this evolution between open and closed models taking shape? Does that influence, Sridhar, what you do at Snowflake?
It does only in an incidental way, at least right now. And the reason for that is the frontier models, the 4 odd companies that make these amazing models, are so much better than everyone else when it comes to key applications like agent tool calling, like coding agents. And so there is very much a demand for that. On the other hand, as things mature, people want to run them at massive scale, which is where open models become more and more important. The one thing that we all need to remember now as a country, as a hemisphere, is that open models end up influencing developer mindsets enormously. At the end of the day, it's only the few thousand engineers that work at OpenAI that have access to the latest and greatest that OpenAI has, and it's a small environment. What we have seen repeatedly is the power of open platforms to literally attract thousands, millions of developers to work on them, and that can be a positive cycle as well. even in areas like data center development, which you would not think of as being very amenable to open technologies. Meta, Facebook, the company, did pretty well in open sourcing some of their plans because they wanted an environment in which more and more people adopted that. So I think open source has a huge influence on just developer mindset. This is the reason why closed companies
Ready, go!
Welcome to the stage, NVIDIA founder and CEO, Jensen Huang.
Las Vegas. Happy New Year. Welcome to CES. Well, we have about 15 keynotes worth of material to pack in here. I'm so happy to see all of you. You got 3,000 people in this auditorium. There's 2,000 people in the courtyard watching us. There's another 1,000 people apparently in the fourth floor where there were supposed to be NVIDIA show floors, all watching this keynote. And of course, millions around the world are going to be watching this to kick off this new year. Well, every 10 to 15 years, the computer industry resets. A new platform shift happens. From mainframe to PC, PC to internet, internet to cloud, cloud to mobile. Each time, the world of applications target a new platform. That's why it's called a platform shift. You write new applications for a new computer. Except this time, there are two simultaneous platform shifts, in fact, happening at the same time. While we now move to AI, applications are now going to be built on top of AI. At first, people thought AIs are applications, and in fact, AIs are applications, but you're going to build applications on top of AIs. But in addition to that, how you run the software, how you develop the software, fundamentally changed. The entire five-layer stack of the computer industry is being reinvented. You no longer program the software, you train the software. You don't run it on CPUs, you run it on GPUs. And whereas applications were pre-recorded, pre-compiled, and run on your device, now applications understand the context and generate every single pixel, every single token, completely from scratch every single time. Computing has been fundamentally reshaped as a result of accelerated computing, as a result of artificial intelligence. Every single layer of that five-layer cake is now being reinvented. Well, what that means is some $10 trillion or so of the last decade of computing is now being modernized to this new way of doing computing. What that means is hundreds of billions of dollars, a couple of $100 billion in VC funding each year is going into modernize and inventing this new world. And what it means is $100 trillion of industry, several percent of which is R&D budget, is shifting over to artificial intelligence. People ask, where is the money coming from? That's where the money is coming from. The modernization of AI to AI, the shifting of R&D budgets from classical methods to now artificial intelligence methods. Enormous amounts of investments coming into this industry, which explains why we're so busy. And this last year was no difference. This last year was incredible. This last year, there's a slide coming. This is what happens when you don't practice. This is the first keynote of the year. I hope it's your first keynote of the year. Otherwise, you have been pretty busy. This is our first keynote of the year. We're going to get the spider webs out. And so 2025 was an incredible year. It seemed like everything was happening all at the same time, and in fact, it probably was. The first thing, of course, is scaling laws. In 2015, the first language model that I thought was really going to make a difference made a huge difference. It was called BERT. 2017, Transformers came. It wasn't until 5 years later, 2022, that ChatGPT moment happened, and it awakened the world to the possibilities of artificial intelligence. Something very important happened a year after that. The first O1 model from ChatGPT, the first reasoning model, completely revolutionary, invented this idea called test time scaling, which is a very commonsensical thing. Not only did we pre-train a model to learn, we post-train it with our reinforcement learning so that it could learn skills. And now we also have test time scaling, which is another way of saying thinking. You think in real time. Each one of these phases of artificial intelligence requires an enormous amount of compute. And the computing law continued to scale. Large language models continued to get better. Meanwhile, another breakthrough happened. And this breakthrough happened in 2024. Agentic systems started to emerge. In 2025, it started to pervade on top of AI. At first, people thought AIs are applications. And in fact, AIs are applications, but you're going to build applications on top of AIs. But in addition to that, how you run the software, how you develop the software fundamentally changed. The entire five-layer stack of the computer industry is being reinvented. You no longer program the software, you train the software. You don't run it on CPUs, you run it on GPUs. And whereas applications were pre-recorded, pre-compiled, and run on your device, now applications understand the context and generate every single pixel, every single token, completely from scratch every single time. Computing has been fundamentally reshaped as a result of accelerated computing, as a result of artificial intelligence. Every single layer of that five-layer cake is now being reinvented. Well, what that means is some 10 trillion. In the case of physical AI, you have AI that interacts with the physical world, and you have AI physics, AI that understands the laws of physics. And then lastly, one of the most important things that happened last year, the advancement of open models. We can now know that AI is going to proliferate everywhere when open source, when open innovation, when innovation across every single company and every industry around the world is activated at the same time. Open models really took off last year. In fact, last year, we saw the advance of DeepSeek R1, the first open model that's a reasoning system. It caught the world by surprise, and it activated, literally, this entire movement. It's really, really exciting work. We're so happy with it. Now, we have open model systems all over the world of all different kinds, and we now know that open models have also reached the frontier. Still solidly is 6 months behind the frontier models, but every single 6 months, a new model is emerging, and these models are getting smarter and smarter. Because of that, you could see the number of downloads has exploded. The number of downloads is growing so fast because startups want to participate in the AI revolution. Large companies want to, researchers want to, students want to, just about every single country wants to. How is it possible that intelligence, the digital form of intelligence, will leave anyone behind? And so open models has really revolutionized artificial intelligence last year. This entire industry is going to be reshaped as a result of that. Now, we had this inkling some time ago. You might have heard that several years ago, we just started to build and operate our own AI supercomputers. We call them DGX clouds. A lot of people asked, are you going into the cloud business? The answer is no. We're building these DGX supercomputers for our own use. Well, it turns out we have billions of dollars of supercomputers in operation so that we could develop our open models. I am so pleased with the work that we're doing. It is starting to attract attention all over the world and all over the industries because we are doing frontier AI model work in so many different domains. The work that we did in proteins, in digital biology, La Proteina to be able to synthesize and generate proteins, OpenFold 3 to understand the structure of proteins, Evo2, how to understand and generate multiple proteins, otherwise the beginnings of cellular representation. Earth-2, AI that understands the laws of physics. The work that we did with ForecastNet, the work that we did with CorrDiff, really revolutionized the way that people are doing weather prediction. Nemotron, we're now doing groundbreaking work there. The first hybrid transformer SSM model that's incredibly fast and therefore can think for a very long time or can think very quickly for not a very long time and produce very, very smart, intelligent answers. Nemotron 3 is groundbreaking work, and you can expect us to deliver other versions of Nemotron 3 in the near future. Cosmos, a frontier, open, world foundation model, one that understands how the world works. Groot, a humanoid robotic system, articulation, mobility, locomotion. These models, these technologies are now being integrated, and in each one of these cases, open to the world. frontier humanoid robotics models open to the world. And then today, we're going to talk a little bit about Alpamayo, the work that we've been doing in self-driving cars. Not only do we open source the models, we also open source the data that we use to train those models. Because only in that way can you truly trust how the models came to be. We open source all the models. We help you make derivatives from them. We have a whole suite of libraries. We call the NEMO libraries, physics NEMO libraries, and the Clara NEMO libraries, each bio NEMO libraries. Each one of these libraries are life cycle management systems of AIs, so that you could process the data, you could generate data, you could train the model, you could create the model, evaluate the model, guardrail the model, all the way to deploying the model. Each one of these libraries are incredibly complex, and all of it is open sourced. And so now, on top of this platform, NVIDIA is a frontier AI model builder. And we build it in a very special way. We build it completely in the open so that we can enable every company, every industry, every country to be part of this AI revolution. I'm incredibly proud of the work that we're doing there. In fact, if you notice the charts, the chart shows that our contribution to this industry is bar none. And you're going to see us, in fact, continue to do that, if not accelerate. These models are also world-class. All systems are down. This never happens in Santa Clara. Is it because of Las Vegas? Somebody must have won a jackpot outside. All systems are down. Okay, I think my system's still down, but that's okay. I'll make it up as I go. And so not only are these models frontier capable, not only are they open, they're also top the leaderboards. This is an area where we're very proud. They top leaderboards in intelligence. We have important models that understand multimodality documents, otherwise known as PDFs. The most valuable content in the world are captured in PDFs. But it takes artificial intelligence to find out what's inside, interpret what's inside, and help you read it. And so our PDF retrievers, our PDF parsers are world-class. Our speech recognition models, absolutely world-class. Our retrieval models, basically search, semantic search, AI search, the database engine of the modern AI era, world-class. So we're on top of leaderboards constantly. This is an area we're very proud of. And all of that is in service of your ability to build AI agents. This is really a groundbreaking area of development. You know, at first when ChatGPT came out, people said, you know, gosh, it produced really interesting results, but it hallucinated greatly. And the reason why it hallucinated, of course, it could memorize everything in the past, but it can't memorize everything in the future, in the current. And so it needs to be grounded in research. It has to do fundamental research before it answers a question. The ability to reason about, do I have to do research? Do I have to use tools? How do I break up a problem into steps? Each one of these steps, something that the AI model knows how to do, and together it is able to compose it into a sequence of steps to perform something it's never done before, never been trained to do. This is the wonderful capability of reasoning. We can encounter a circumstance we've never seen before and break it down into circumstances and knowledge or rules that we know how to do because we've experienced it in the past. And so the ability for AI models now to be able to reason, incredibly powerful. The reasoning capability of agents opened the doors to all of these different applications. We no longer have to train an AI model to know everything on day one, just as we don't have to know everything on day one, that we should be able to, in every circumstance, reason about how to solve that problem. Large language models has now made this fundamental leap. The ability to use reinforcement learning and chain of thought and search and planning and all these different techniques in reinforcement learning has made it possible for us to have this basic capability, and it's also now completely open sourced. But the thing that's really terrific is another breakthrough that happened. And the first time I saw it was with Arvind's Perplexity, the search company, the AI search company, really innovative company. And the first time I realized they were using multiple models at the same time, I thought it was completely genius. Of course we would do that. Of course an AI would also call upon all of the world's great AIs to solve the problem it wants to solve at any part of the reasoning chain. And this is the reason why AIs are really multimodal, meaning they understand speech and images and text and videos and 3D graphics and proteins. It's multimodal. It's also multi-model, meaning that they should be able to use any model that best fits the task. It is multi-cloud by definition, therefore, because these AI models are sitting in all these different places, and it also is hybrid cloud. Because if you're an enterprise company or you built a robot or whatever that device is, sometimes it's at the edge, sometimes a radio cell tower, maybe sometimes it's in an enterprise, or maybe it's a place where a hospital where you need to have the data in real time right next to you. Whatever those applications are, we know now this is what an AI application looks like in the future. Or another way to think about that, because future applications are built on AIs, this is the basic framework of future applications. This basic framework, this basic structure of agentic AIs that could do the things that I'm talking about, that is multi-model, has now turbocharged AI startups of all kinds. And now you can also, because of all of the open models and all the tools that we provided you, you could also customize your AIs to teach your AI skills that nobody else is teaching. Nobody else is causing their AI to become intelligent or smart in that way. You could do it for yourself. And that's the work that we do with Nemotron, Nemo, and all of the things that we do with open models is intended to do. You put a smart router in front of it, and that router is essentially a manager that decides which one of the tasks, based on the intention of the prompts that you give it, which one of the models is best fit for that application, for that solving that problem. Okay? So now, when you think about this architecture, what do you have? When you think about this architecture, all of a sudden you have an AI that's on the one hand, completely customizable by you. Something that you could teach to do your own very skills for your company. Something that's domain secret. Something where you have deep domain expertise. Maybe you've got all of the data that you need to train that AI model. On the other hand, your AI is always at the frontier, by definition. You're always at the frontier on the one hand, you're always customized on the other hand, and it should just run. And so we thought we would make the simplest of examples to make it available to you. This entire framework we call a blueprint. And we have blueprints that are integrated into enterprise SaaS platforms all over the world, and we're really pleased with the progress. But what we do is show you a short example of something that anybody can do.
Let's build a personal assistant. I want it to help me with my calendar, emails, to-do lists, and even keep an eye on my home. I use Brev to turn my DGX Spark into a personal cloud. So I can use the same interface whether I'm using a cloud GPU or a DGX Spark. I use a Frontier Model API to easily get started. I wanted to help me with my emails, so I create an email tool for my agent to call. I want my emails to stay private, so I'll add an open model that's running locally on the Spark. Now for any job, I want the agent to use the right model for the right task, so I'll use an intent-based model router. This way, prompts that need email will stay on my Spark, and everything else can call the Frontier model. I want my assistant to interact with my world, so I'll hook it up to Hugging Face's Reachy mini robot. My agent controls the head, ears, and camera of the Reachy with tool calls. I want to give Reachy a voice, and I really like 11 Labs, so I'll hook up their API.
Hi, I'm Reachy, running on DGX Spark.
Hey Reachy, what's on my to-do list today?
Your to-do list today. Grab groceries, eggs, milk, butter, and send Jensen the new script.
Okay, let's send Jensen that update. Tell him we'll have it for him by the end of the day.
Will do.
Reachy, there's a sketch too. Can you turn it into an architectural rendering?
Sure.
Nice. Now make a video and show me around the room.
Here you go.
That's great. With Brev, I can share access to my Spark and Ricci, so I'm going to share it with Anna.
Hey Ricci, what's Potato up to?
He's on the couch. I remember you don't like this. I'll tell him to get off. Potato, off the couch.
With all the progress in open source, it's incredible to see what you can build. I'd love to see what you create.
Isn't that incredible? Now, the amazing thing is, that is utterly trivial now. That is utterly trivial now. And yet, just a couple of years ago, all of that would have been impossible. Absolutely unimaginable. Well, this basic framework, this basic way of building applications, using language models, using language models that are pre-trained and they're proprietary, they're frontier, combine it with customized language models into a agentic framework, a reasoning framework that allows you to access tools and files and maybe even connect to other agents. This is basically the architecture of AI applications or applications in the modern age. And the ability for us to create these applications are incredibly fast. And notice, if you give it this application information that it's never seen before, or in a structure that is not represented exactly as you thought, it can still reason through it and make its best effort to reason through the data, the information, to try to understand how to solve the problem. Artificial intelligence. Okay, so this basic framework is now being integrated, and everything that I just described, we have the benefit of working with some of the world's leading enterprise platform companies. Palantir, for example, their entire AI and data processing platform is being integrated and accelerated by NVIDIA today. ServiceNow, the world's leading customer service and employee service platform. Snowflake, the world's top data platform in the cloud. Incredible work that is being done there. CodeRabbit, we're using CodeRabbit all over NVIDIA. CrowdStrike, creating AIs to detect, to find AI threats. NetApp, their data platform now has NVIDIA's semantic AI on top of it and agentic systems on top of it for them to do customer service. But the important thing is this. Not only is this the way that you develop applications now, this is going to be the user interface of your platform. So whether it's Palantir or ServiceNow or Snowflake and many other companies that we're working with, the agentic system is the interface. It's no longer Excel with a bunch of squares that you enter information into. Maybe it's no longer just command line. All of that multimodality information is now possible, and the way you interact with your platform is much more, well, if you will, simple, like you're interacting with people. And so that's enterprise AI being revolutionized by agentic systems. The next thing is physical AI. This is an area that you've seen me talk about for several years. In fact, we've been working on this for 8 years. The question is, how do you take something that is intelligent inside a computer and interacts with you with screens and speakers to something that can interact with the world, meaning it can understand the common sense of how the world works. Object permanence. If I look away and I look back, that object is still there. Causality. If I push it, it tips over. It understands friction and gravity. It understands inertia. That a heavy truck rolling down the road is going to need a little bit more time to stop. That a ball is going to keep on rolling. These ideas are common sense to even a little child, but for AI, it's completely unknown. And so we have to create a system that allows AIs to learn the common sense of the physical world, learn its laws, but also to be able to, of course, learn from data, and the data is quite scarce, and to be able to evaluate whether that AI is working, meaning it has to simulate in an environment. How does an AI know that the actions that it's performing is consistent with what it should do if it doesn't have the ability to simulate the response of the physical world back on its actions? The response of its actions is really important to simulate. Otherwise, there's no way to evaluate it. It's different every time. And so this basic system requires 3 computers. One computer, of course, the one that we know that NVIDIA built for training the AI models. Another computer that we know is to inference the models. Inferencing the model is essentially a robotics computer that runs in a car or runs in a robot or runs in a factory, runs anywhere at the edge. But there has to be another computer that's designed for simulation. And simulation is at the heart of almost everything NVIDIA does. This is where we are most comfortable. And simulation was really the foundations of almost everything that we've done with physical AI. So we have 3 computers and multiple stacks that run on these computers, these libraries, to make them useful. Omniverse is our digital twin, physically based simulation world. Cosmos, as I mentioned earlier, is our foundation model, not a foundation model for language, but a foundation model of the world. And it's also aligned with language. You could say something like, what's happening to the ball? And they'll tell you the ball's rolling down the street. And so a world foundation model, and then of course the robotics models. We have 2 of them. One of them is called Groot. The other one's called Alpamayo that I'm going to tell you about. Now, one of the most important things that we have to do with physical AI is to create the data to train the AI in the first place. Where does that data come from? Rather than, instead of having languages, because we created a bunch of text that are what we consider ground truth that the AI can learn from, how do we teach an AI the ground truth of physics? There are lots and lots of videos, but hardly enough to capture the diversity and the type of interactions that we need. And so this is where great minds came together and transformed what used to be compute into data. Now, using synthetic data generation that is grounded and conditioned by the laws of physics, grounded and conditioned by ground truth, we can now selectively, cleverly generate data that we can then use to train the AI. So for example, what comes into this AI, this Cosmos AI world model on the left, over here, is the output of a traffic simulator. Now this traffic simulator is hardly enough for an AI to learn from. We can take this, put it into a Cosmos foundation model, and generate surround video that is physically based and physically plausible that the AI can now learn from. And there are so many examples of this. Let me show you what Cosmos can do.
The ChatGPT moment for physical AI is nearly here. But the challenge is clear. The physical world is diverse and unpredictable. Collecting real-world training data is slow and costly, and it's never enough. The answer is synthetic data. It starts with NVIDIA Cosmos, an open, frontier world foundation model for physical AI. Pre-trained on internet-scale video, real driving and robotics data, and 3D simulation. Cosmos learned a unified representation of the world, able to align language, images, 3D, and action. It performs physical AI skills like generation, reasoning, and trajectory prediction. From a single image, Cosmos generates realistic video. From 3D scene descriptions, physically coherent motion. From driving telemetry and sensor logs, surround video. From planning simulators, multi-camera environments. Or from scenario prompts, it brings edge cases to life. Developers can run interactive closed-loop simulations in Cosmos. When actions are made, the world responds. Cosmos Reasons. It analyzes edge scenarios, breaks them down into familiar physical interactions, and reasons about what could happen next. Cosmos turns compute into data, training AVs for the long tail, and robots how to adapt for every scenario.
I know, it's incredible. Cosmos is the world's leading foundation model, world foundation model. It's been downloaded millions of times, used all over the world, getting the world ready for this new era of physical AI. We use it ourselves as well. We use it ourselves to create our self-driving car, using it for scenario generation and using it for evaluation. We could have something that allows us to effectively travel billions, trillions of miles, but doing it inside a computer. And we've made enormous progress. Today, we're announcing Alpamayo, the world's first thinking, reasoning, autonomous vehicle AI. Alpamayo is trained end to end, literally from camera in to actuation out. The camera in, lots and lots of miles that are driven by itself, where we human drive it, using human demonstration. And we have lots and lots of miles that are generated by Cosmos. In addition to that, hundreds of thousands of examples are labeled very, very carefully so that we could teach the car how to drive. Alpamayo does something that's really special. Not only does it take sensor input and activates steering wheel, brakes, and acceleration, it also reasons about what action it is about to take. It tells you what action it's going to take, the reasons by which it came about that action, and then, of course, the trajectory. All of these are coupled directly and trained very specifically by a large combination of human-trained and as well as Cosmos-generated data. The result of it is just really incredible. Not only does your car drive as you would expect it to drive, and it drives so naturally because it learned directly from human demonstrators, but in every single scenario, when it comes up to the scenario, it reasons about, it tells you what it's going to do, and it reasons about what's about to do. Now, the reason why this is so important is because of the long tail of driving. It's impossible for us to simply collect every single possible scenario for everything that could ever happen in every single country, in every single circumstance that's possibly ever going to happen for all of population. However, it is very likely that every scenario, if decomposed into a whole bunch of other smaller scenarios, are quite normal for you to understand. And so these long tails will be decomposed into quite normal circumstances that the car knows how to deal with. It just needs to reason about it. And so let's take a look. Everything you're about to see is one shot. It's no hands.
Routing to your destination. Buckle up. You have arrived.
We started working on self-driving cars 8 years ago, and the reason for that is because we reasoned early on that deep learning and artificial intelligence was going to reinvent the entire computing stack. And if we were ever going to understand how to navigate ourselves and how to guide the industry towards this new future, we have to get good at building the entire stack. Well, as I mentioned earlier, AI is a 5-layer cake. The lowest layer is land, power, and shell. In the case of robotics, the lowest layer is the car. The next layer above it is chips. GPUs, networking chips, CPUs, all that kind of stuff. The next layer above that is the infrastructure. That infrastructure, in this particular case, as I mentioned with physical AI, is Omniverse and Cosmos. And then above that are the models. And in the case of the models above that I've just shown you, the model here is called AlphaMayo. And AlphaMayo today is open sourced. This incredible body of work, it took several thousand people. Our AV team is several thousand people, just to put in perspective. Our partner, Ola, I think Ola's here in the audience somewhere, Mercedes, agreed to partner with us 5 years ago to go make all of this possible. We imagine that someday 1 billion cars on the road will all be autonomous. You could either have it be a robo-taxi that you're orchestrating and renting from somebody, or you could own it and it's driving by itself. Or you could decide to drive for yourself. And so, but every single car will have autonomous vehicle capability. Every single car will be AI powered. And so the model layer in this case is AlphaMayo, and the application above that is the Mercedes-Benz. Okay, and so this entire stack is our first NVIDIA first entire stack endeavor. And we've been working on it for this entire time, and I'm just so happy that the first AV car from NVIDIA is going to be on the road in Q1, and then it goes Europe in Q2, here in the United States in Q1, then Europe in Q2, and I think it's Asia in Q3 and Q4. And the powerful thing is that we're going to keep on updating it with next versions of AlphaMayo and versions after that. There's no question in my mind now that this is going to be one of the largest robotics industries, and I'm so happy that we worked on it. And it taught us an enormous amount about how to help the rest of the world build robotic systems. That deep understanding and knowing how to build it ourselves, building the entire infrastructure ourselves, and knowing what kind of chips a robotic system would need. In this particular case, dual Orins, the next generation dual Thors. These processors are designed for robotic systems and was designed for the highest level of safety capability. This car just got rated. It just went to production. The Mercedes-Benz CLA was just rated by NCAP, the world's safest car. It is the only system that I know that has every single line of code, the chip, the system, every line of code, safety certified. The entire model system is based on sensors are diverse and redundant, and so is the self-driving car stack. The AlphaMayo stack is trained end-to-end and has incredible skills. However, nobody knows until you drive it forever that it's going to be perfectly safe. And so the way we guardrail that is with another software stack, an entire AV stack underneath. That entire AV stack is built to be fully traceable. And it's taken us some 5 years to build that, some 6, 7 years actually, to build that second stack. These two software stacks are mirroring each other. And then we have a policy and safety evaluator decide, is this something that I'm very confident and can reason about driving very safely? If so, I'm going to have AlphaMayo do it. If it's a circumstance that I'm not very confident in, and the safety policy evaluator decide that we're going to go back to a simpler, safer guardrail system, then it goes back to the classical AV stack. We're the only car in the world with both of these AV stacks running, and all safety systems should have diversity and redundancy. Well, our vision is that someday, every single car, every single truck will be autonomous. And we've been working towards that future. This entire stack is vertically integrated, of course, in the case of Mercedes-Benz. We built the entire stack together. We're going to deploy the car. We're going to operate the stack. We're going to maintain the stack for as long as we shall live. However, like everything else we do as a company, we build the entire stack, but the entire stack is open for the ecosystem. And the ecosystem working with us to build L4 and robo-taxis is expanding, and it's going everywhere. I fully expect this to be, well, this is already a giant business for us. It's a giant business for us because they use it for training data, processing data, and training their models. They use it for synthetic data generation in some cases. In some companies, they pretty much just build the computers, the chips that are inside the car. And some companies work with us full stack. Some companies work with us some partial part of that. Okay, so it doesn't matter how much you decide to use. You know, my only request is to use a little bit of video wherever you can, and but the entire thing is open. Now, this is going to be the first large-scale, mainstream AI, physical AI market, and this is now, I think we can all agree, fully here. And this inflection point of going from not autonomous vehicles to autonomous vehicles is probably happening right about this time. In the next 10 years, I'm fairly certain a very, very large percentage of the world's cars will be autonomous or highly autonomous. But this basic technique that I just described in using the 3 computers, using synthetic data generation and simulation applies to every form of robotic systems. It could be a robot that is just an articulator, a manipulator. Maybe it's a mobile robot. Maybe it's a fully humanoid robot. And so the next journey, the next era for robotic systems is going to be, robots. And these robots are going to come in all kinds of different sizes. And I invited some friends. Did they come? Hey, guys. Hurry up. I got a lot of stuff to cover. Come on, hurry. Did you tell R2-D2 you're going to be here? Did you? And C-3PO? Okay, all right, come here. Now, one of the things that's really, you have Jetsons. They have little Jetson computers inside them. They're trained inside Omniverse. And how about this? Let's show everybody the simulator that you guys learned how to be robots in. You guys want to look at that? Okay, let's look at that. Run it, please. Isn't that amazing? That's how you learn to be a robot. You did it all inside Omniverse. And the robot simulator is called Isaac. Isaac Sim and Isaac Lab. And anybody who wants to build a robot, nobody's going to be as cute as you. But now we have look at all these friends that we have building robots. We're building big ones. Like I said, nobody's as cute as you guys are. But we have Neurobot and we have Agibot over there. We have LG over here. They just announced a new robot. Caterpillar, they've got the largest robots ever. That one delivers food to your house. That's connected to Uber Eats, and that's Surf Robot. I love those guys. Agility, Boston Dynamics, incredible. You got surgical robots. You got manipulated robots from Franca. You got universal robotics robot. Incredible number of different robots. And so this is the next chapter. We're going to talk a lot more about robotics in the future. But it's not just about the robots in the end. I know everything's about you guys. It's about getting there. And one of the most important industries in the world that will be revolutionized by physical AI and AI physics is the industry that started all of us. At NVIDIA, it wouldn't be possible if not for the companies that I'm about to talk to, and I'm so happy that all of them, starting with Cadence, is going to accelerate everything Cadence. CUDA-X integrated into all of their simulations and solvers. They've got NVIDIA physical AIs that they're going to use for different physical plants and plant simulations. You got AI physics being integrated into these systems. So whether it's an EDA or SDA, and in the future robotic systems, we're going to have basically the same technology that made you guys possible. Now completely revolutionize these design stacks. Synopsys. Without Synopsys, Synopsys and Cadence are completely indispensable in the world of chip design. Synopsys leads in logic design and IP. In the case of Cadence, they lead physical design, the place and route, and emulation and verification. Cadence is incredible at emulation and verification. Both of them are moving into the world of system design and system simulation. And so in the future, we're going to design your chips inside Cadence and inside Synopsys. We're going to design your systems and emulate the whole thing and simulate everything inside these tools. That's your future. We're going to you're going to be born inside these platforms. Pretty amazing, right? And so we're so happy that we're working with these industries. Just as we've integrated NVIDIA into Palantir and ServiceNow, we're integrating NVIDIA into the most computationally intensive simulation industries, Synopsys and Cadence. And today we're announcing that Siemens is also doing the same thing. We're going to integrate CUDA-X, physical AI, agentic AI, NeMo, Nemotron, deeply integrated into the world of Siemens. And the reason for that is this. First, we designed the chips, and all of it in the future will be accelerated by NVIDIA. You're going to be very happy about that. We're going to have agentic chip designers and system designers working with us, helping us do design, just as we have agentic software engineers helping our software engineers code today. And so we'll have agentic chip designers and system designers. We're going to create you inside this. But then we have to build you. We have to build the plants, the factories that manufacture you. We have to design the manufacturing lines that assemble all of you. And these manufacturing plants are going to be essentially gigantic robots. Incredible, isn't that right? I know. And so you're going to be designed in a computer. You're going to be made in a computer. You're going to be tested and evaluated in a computer long before you have to spend any time dealing with gravity. I know. Do you know how to deal with gravity? Can you jump? Can you jump? Okay, all right, don't show off. Okay, so now the industry that made NVIDIA possible, I'm just so happy that now the technology that we're creating is at a level of sophistication and capability that we can now help them revolutionize their industry. And so what started with them, we now have the opportunity to go back and help them revolutionize theirs. Let's take a look at the stuff that we're going to do with Siemens. Come on.
Breakthroughs in physical AI are letting AI move from screens to our physical world. And just in time, as the world builds factories of every kind for chips, computers, life-saving drugs, and AI. As the global labor shortage worsens, we need automation powered by physical AI and robotics more than ever. This, where AI meets the world's largest physical industries, is the foundation of NVIDIA and Siemens' partnership. For nearly 2 centuries, Siemens has built the world's industries. And now, it is reinventing it for the age of AI. Siemens is integrating NVIDIA CUDA-X libraries, AI models, and Omniverse into its portfolio of EDA, CAE, and digital twin tools and platforms. Together, we're bringing physical AI to the full industrial lifecycle. From design and simulation to production and operations. We stand at the beginning of a new industrial revolution, the age of physical AI, built by NVIDIA and Siemens for the next age of industries.
Incredible, right, guys? What do you think? All right, I'll hang on tight. Just hang on tight. And so this is, if you look at the world's models, there's no question OpenAI is the leading token generator today. More OpenAI tokens are generated than just about anything else. The second largest is probably open models. And my guess is that over time, because there are so many companies, so many researchers, so many different types of domains and modalities, that open source models will be by far the largest. Let's talk about somebody really special. You guys want to do that? Let's talk about Vera Rubin. Vera Rubin, yeah, go ahead. She's an American astronomer. She was the first to observe. She noticed that the tails of the galaxies were moving about as fast as the center of the galaxies. Well, I know, it makes no sense. It makes no sense. Newtonian physics would say, just like the solar system, the planets further away from the sun is circling the sun slower than the planets closer to the sun. And therefore, it makes no sense that this happens unless there's invisible bodies, we call them, she discovered dark matter, that occupy space even though we don't see it. And so Vera Rubin is the person that we named our next computer after. Isn't that a good idea? I know. Okay, Vera Rubin is designed to address this fundamental challenge that we have. The amount of computation necessary for AI is skyrocketing. The demand for NVIDIA GPUs is skyrocketing. It's skyrocketing because models are increasing by a factor of 10, an order of a magnitude every single year. And not to mention, as I mentioned, O1's introduction was an inflection point for AI. Instead of a one-shot answer, inference is now a thinking process. And in order to teach the AI how to think, reinforcement learning and very significant computation was introduced into post-training. It's no longer supervised fine-tuning, or otherwise known as imitation learning or supervision training. You now have reinforcement learning, essentially the computer trying different iterations itself, learning how to perform a task. The amount of computation for pre-training, for post-training, for test time scaling has exploded as a result of that. And now, every single inference that we do, instead of just one shot, the number of tokens, you could just see the AIs think, which we appreciate. The longer it thinks, oftentimes it produces a better answer. And so test time scaling causes the number of tokens to be generated increase by 5x every single year. Not to mention, meanwhile, the race is on for AI. Everybody's trying to get to the next level. Everybody's trying to get to the next frontier. And every time they get to the next frontier, the last generation AI tokens, the cost starts to decline, about a factor of 10x every year. The 10x decline every year is actually telling you something different. It's saying that the race is so intense. Everybody's trying to get to the next level, and somebody is getting to the next level. And so therefore, all of it is a computing problem. The faster you compute, the sooner you can get to the next level of the next frontier. All of these things are simultaneously happening at the same time. And so we decided that we have to advance the state of the art of computation every single year, not 1 year left behind. And now we've been shipping GB200s a year and a half ago. Right now we're in full-scale manufacturing of GB300. And if Vera Rubin is going to be in time for this year, it must be in production by now. And so today I can tell you that Vera Rubin is in full production. You guys want to take a look at Vera Rubin? All right, come on. Play it, please.
Vera Rubin arrives just in time for the next frontier of AI. This is the story of how we built it. The architecture, a system of 6 chips, engineered to work as one, born from extreme co-design. It begins with Vera, a custom-designed CPU, double the performance of the previous generation, and the Rubin GPU. Vera and Rubin are co-designed from the start to bidirectionally and coherently share data faster and with lower latency. Then, 17,000 components come together on a Vera Rubin compute board. High-speed robots place components with micron precision before the Vera CPU and 2 Rubin GPUs complete the assembly. Capable of delivering 100 petaflops of AI, 5 times that of its predecessor. AI needs data, fast. Connect X9 delivers 1.6 terabits per second of scale-out bandwidth to each GPU. Bluefield 4 DPU offloads storage and security, so compute stays fully focused on AI. The Vera Rubin compute tray, completely redesigned with no cables, hoses, or fans. Featuring a Bluefield 4 DPU, 8 Connect X9 NICs, 2 Vera CPUs, and 4 Rubin GPUs. The compute building block of the Vera Rubin AI supercomputer. Next, the 6th generation NVLink switch. Moving more data than the global internet, connecting 18 compute nodes, scaling up to 72 Rubin GPUs, operating as one. Then, Spectrum X Ethernet Photonics. The world's first Ethernet switch with 512 lanes and 200 gigabit capable co-packaged optics scale out thousands of racks into an AI factory. 15,000 engineer years since design began, the first Vera Rubin NVL72 rack comes online. 6 breakthrough chips, 18 compute trays, 9 NVLink switch trays, 220 trillion transistors, weighing nearly 2 tons. One giant leap to the next frontier of AI. Rubin is here.
What do you guys think? This is a Rubin pod, 1,152 GPUs in 16 racks. Each one of the racks, as you know, has 72 Vera Rubin, or 72 Rubins. Each one of the Rubins is 2 actual GPU dies connected together. I'm going to show it to you. But there are several things that, well, I'll tell you later. I can't tell you everything right away. Well, we designed 6 different chips. First of all, we have a rule inside our company, and it's a good rule. No new generation should have more than 1 or 2 chips change. But the problem is this. As you could see, we were describing the total number of transistors in each one of the chips that were being described, and we know that Moore's law has largely slowed. And so the number of transistors we can get year after year after year can't possibly keep up with the 10 times larger models. It can't possibly keep up with 5 times per year more tokens generated. It can't possibly keep up with the fact that cost decline of the tokens are going to be so aggressive. It is impossible to keep up with those kind of rates if for the industry to continue to advance unless We deployed aggressive, extreme co-design, basically innovating across all of the chips, across the entire stack, all at the same time, which is the reason why we decided that this generation, we had no choice but to design every chip over again. Now, every single chip that we were describing just now can be a press conference in all in itself. And there's an entire company who's probably dedicated to doing that back in the old days. Each one of them are completely revolutionary and the best of its kind. The Vera CPU, I'm so proud of it. In a power-constrained world, Grace CPU is 2 times the performance. In a power-constrained world, it's twice the performance per watt of the world's most advanced CPUs. Its data rate is insane. It was designed to process supercomputers. And Vera was an incredible GPU. Grace was an incredible GPU. Now Vera increases the single-threaded performance, increases the capacity of the memory, increases everything just dramatically. It's a giant chip. This is the Vera CPU. This is one CPU. And this is connected to the Rubin GPU. Look at that thing. It's a giant chip. Now, the thing that's really special, and I'll go through these. It's going to take 3 hands, I think, 4 hands to do this. Okay, so this is the Vera CPU. It's got 88 CPU cores, and the CPU cores are designed to be multi-threaded. But the multi-threaded nature of Vera was designed so that each one of the 176 threads could get its full performance. So it's essentially as if there's 176 cores, but only 88 physical cores. So these cores were designed in using a technology called spatial multi-threading. But the I/O performance is incredible. This is the Rubin GPU. It's 5x Blackwell in floating performance. But the important thing is go to the bottom line. The bottom line, it's only 1.6 times the number of transistors of Blackwell. That kind of tells you something about the levels of semiconductor physics today. If we don't do co-design, if we don't do extreme co-design at the level of basically every single chip across the entire system, how is it possible we deliver performance levels that is, at best 1.6 times each year? Because that's the total number of transistors you have. And even if you were to have a little bit more performance per transistor, say 25%, it's impossible to get 100% yield out of the number of transistors you get. And so 1.6x kind of puts a ceiling on how far performance can go each year unless you do something extreme, and we call it extreme co-design. Well, one of the things that we did, and it was a great invention, is called NVFP4 Tensor Core. The transformer engine inside our chip is not just a 4-bit floating point number somehow that we put into the data path. It is an entire processor, a processing unit that understands how to dynamically, adaptively adjust its precision and structure to deal with different levels of the transformer so that you can achieve higher throughput wherever it's possible to lose precision and to go back to the highest possible precision wherever you need to. That ability to dynamically do that, you can't do this in software because obviously it's just running too fast. And so you have to be able to do it adaptively inside the processor. That's what an NVFP4 is. When somebody says FP4 or FP8, it almost means nothing to us. And the reason for that is because it's the tensor core structure and all of the algorithms that makes it work. NVFP4, we've published papers on this already. The precision, the level of throughput and precision it's able to retain is completely incredible. This is groundbreaking work. I would not be surprised if the industry would like us to make this format and this structure an industry standard in the future. This is completely revolutionary. This is how we were able to deliver such a gigantic step up in performance, even though we only have 1.6 times the number of transistors. Okay, so this is, and now once you have a great processing node, and this is the processor node, and inside, so this is for example, here, let me do this. This is, wow, it's super heavy. You have to be a CEO in really good shape to do this job. Okay, all right. So this thing is, I'm gonna guess, this is probably, I don't know, a couple of 100 pounds. I thought that was funny too. Come on. It could have been. Everybody's going, no, I don't think so. All right, so look at this. This is the last one. We revolutionized the entire MGX chassis. This node, 43 cables, 0 cables, 6 tubes, just 2 of them here. It takes 2 hours to assemble this. If you're lucky, it takes 2 hours. And of course, you're probably going to assemble it wrong. You're going to have to retest it, test it, reassemble it. So the assembly process is incredibly complicated. And it was understandable as one of our first supercomputers that's deconstructed in this way. This, from 2 hours to 5 minutes. %, liquid cooled, 100% liquid cooled. Yeah, really, really a breakthrough. Okay, so this is the new compute chassis, and what connects all of these to the top of rack switches, the east-west traffic, is called the Spectrum-X NIC. This is the world's best NIC, unquestionably NVIDIA's Mellanox, the acquisition Mellanox that joined us a long time ago now. Their networking technology for high-performance computing is the world's best, bar none. The algorithms, the chip design, all of the interconnects, all the software stacks that run on top of it, their RDMA, absolutely bar none, the world's best. And now it has the ability to do programmable RDMA and data path accelerator so that our partners like AI Labs could create their own algorithms for how they want to move data around the system. But this is completely world-class, ConnectX. ConnectX 9 and the Vera CPU were co-designed, and we never revealed it, never released it until CX9 came along, because we co-designed it for a new type of processor. You know, ConnectX 9, or CX8 and Spectrum-X, revolutionized how Ethernet was done for artificial intelligence. Ethernet traffic for AI is much more intense, requires much lower latency. The instantaneous surge of traffic is unlike anything Ethernet sees. And so we created Spectrum-X, which is AI Ethernet. 2 years ago, we announced Spectrum-X. NVIDIA today is the largest networking company the world has ever seen. So it's been so successful and used in so many different installations. It is just sweeping the AI landscape. The performance is incredible, especially when you have a 200 megawatt data center, or if you have a gigawatt data center. These are billions of dollars. Let's say a gigawatt data center is $50 billion. If the networking performance allows you to deliver an extra 10%, in the case of Spectrum-X, delivering 25% higher throughput is not uncommon. If we were to just deliver 10%, that's worth $5 billion. The networking is completely free, which is the reason why, well, everybody uses Spectrum-X. It's just an incredible thing. And now we're going to invent a new type of data processing. And so Spectrum-X is for east-west traffic. We now have a new processor called BlueField-4. BlueField-4 allows us to take a very large data center, isolate different parts of it so that different users could use different parts of it, make sure that everything could be virtualized if they decide to be virtualized. So you offload a lot of the virtualization software, the security software, the networking software for your north-south traffic. And so BlueField-4 comes standard with every single one of these compute nodes. BlueField-4 has a second application I'm going to talk about in just a second. This is a revolutionary processor, and I'm so excited about it. This is the NVLink 6 switch, and it's right here. This is this switch chip. There are 4 of them inside the NVLink switch here. Each one of these switch chips has the fastest SerDes in history. The world is barely getting to 200 gigabits. This is 400 gigabits per second switch. The reason why this is so important is so that we could have every single GPU talk to every other GPU at exactly the same time. This switch on the backplane of one of these racks enables us to move the equivalent of twice the amount of the global internet data, all of the world's internet data at twice the speed. You take the cross-sectional bandwidth of the entire planet's internet, it's about 100 terabytes per second. This is 240 terabytes per second. So it kind of puts it in perspective. This is so that every single GPU can work with every single other GPU at exactly the same time. Okay? Then on top of that, okay, so this is one rack. This is one rack. Each one of the racks, as you can see, the number of transistors in this one rack is 1.7 times. Yeah, could you do this for me? So this is, it's usually about 2 tons, but today it's 2.5 tons because when they shipped it, they forgot to drain the water out of it. So we shipped a lot of water from California. Can you hear it squealing? You know, when you're rotating 2.5 tons, you're gonna squeal a little. Oh, you could do it. Wow. Okay, we won't make you do that twice. All right, so behind this are the NVLink spines. Basically 2 miles of copper cables. Copper is the best conductor we know. And these are all shielded copper cables, structured copper cables, the most the world's ever used in computing systems ever. And our SerDes drive the copper cables from the top of the rack all the way to the bottom of the rack at 400 gigabits per second. It's incredible. And so this has 2 miles of total copper cables, 5,000 copper cables, and this makes the NVLink spine possible. This is the revolution that really started the NGX system. Now, we decided that we would create an industry standard system so that the entire ecosystem, all of our supply chain, could standardize on these components. There are some 80,000 different components that make up these NGX systems, and it's a total waste if we were to change it every single year. Every single major computer company, from Foxconn to Quanta to Wistron, you know, the list goes on and on and on, to HP and Dell and Lenovo, everybody knows how to build these systems. And so the fact that we could squeeze Vera Rubin into this, even though the performance is so much higher, and very importantly, the power is twice as high. The power of Vera Rubin is twice as high as Grace Blackwell. And yet, and this is the miracle, the air that goes into it, the air flow is about the same. And very importantly, the water that goes into it is the same temperature, 45 degrees C. With 45 degrees C, no water chillers are necessary for data centers. We're basically cooling this supercomputer with hot water. It is so incredibly efficient. And so this is the new rack. 1.7 times more transistors, but 5 times more peak inference performance, 3.5 times more peak training performance. Okay? They're connected on top using Spectrum-X. Oh, thank you. This is the world's first manufacturing chip using TSMC's new process that we co-innovated called COUP. It's a integrated silicon photonics process technology. And this allows us to take silicon photonics directly right to the chip. And this is 512 ports at 200 gigabits per second. And this is the new Ethernet AI switch, the Spectrum-X Ethernet switch. And look at this giant chip. But what's really amazing is it's got silicon photonics directly connected to it. And lasers come in. Lasers come in through here. Lasers come in through here. The optics are here, and they connect out to the rest of the data center. This I'll show you in a second, but this is on top of the rack. And this is the new Spectrum-X silicon photonics switch. Okay? And we have something new I want to tell you about. So just as I mentioned, a couple of years ago, we introduced Spectrum-X so that we could reinvent the way that networking is done. Ethernet is really easy to manage, and everybody has an Ethernet stack, and every data center in the world knows how to deal with Ethernet. And the only thing that we were using at the time was called InfiniBand, which is used for supercomputers. InfiniBand is very low latency, but of course the software stack, the entire manageability of InfiniBand is very alien to the people who use Ethernet. So we decided to enter the Ethernet switch market for the very first time. Spectrum-X, that just took off, and it made us the largest networking company in the world, as I mentioned. This next generation Spectrum-X is going to carry on that tradition. But just as I said earlier, AI has reinvented the whole computing stack, every layer of the computing stack. It stands to reason that when AI starts to get deployed in the world's enterprises, it's going to also reinvent the way storage is done. Well, AI doesn't use SQL, AI uses semantics information. And when AI is being used, it creates this temporary knowledge, temporary memory called KV cache, key value combinations, but it's a KV cache, basically the cache of the AI, the working memory of the AI. And the working memory of the AI is stored in the HBM memory. Every single token, for every single token, the GPU reads in the model, the entire model. It reads in the entire working memory, and it produces one token. And it stores that one token back into the KV cache. And then the next time it does that, it reads in the entire memory, reads it, and it streams it through our GPU, and then generates another token. Well, it does this repeatedly, token after token after token, and obviously, if you have a long conversation with that AI, over time, that memory, that context memory is going to grow tremendously. Not to mention the models are growing, the number of turns that we're using, the AIs are increasing. We would like to have this AI stay with us our entire life and remember every single conversation we've ever had with it, right? Every single lick of research that I've asked it for. Of course, with the number of people that will be sharing the supercomputer is going to continue to grow. And so this context memory, which started out fitting inside an HBM, is no longer large enough. Last year, we created Grace Blackwell's very fast memory, we call fast context memory. That's the reason why we connected Grace directly to Hopper. That's why we connected Grace directly to Blackwell, so that we can expand the context memory. But even that is not enough. And so the next solution, of course, is to go off onto the network, the north-south network, off to the storage of the company. But if you have a whole lot of AIs running at the same time, that network is no longer going to be fast enough. So the answer is very clearly to do it different. And so we created BlueField 4 so that we could essentially have a very fast KV cache context memory store right in the rack. And so I'll show you in just one second, but there's a whole new category of storage systems. And the industry is so excited because this is a pain point for just about everybody who does a lot of token generation today. The AI labs, the cloud service providers, they're really suffering from the amount of network traffic that's being caused by KV cache moving around. And so the idea that we would create a new platform, a new processor, to run the entire Dynamo KV cache context memory management system and to put it very close to the rest of the rack is completely revolutionary. So this is it. It sits right here. So this is all the compute nodes. Each one of these is NVLink 72. So this is Vera Rubin, NVLink 72, 144 Rubin GPUs. This is the context memory that's stored here. Behind each one of these are 4 BlueFields. Behind each BlueField is 150 terabytes of memory, context memory. And for each GPU, once you allocate it across, each GPU will get an additional 16 terabytes. Now, inside this node, each GPU essentially has 1 terabyte. And now, with this backing store here, directly on the same east-west traffic, Express, every NVLink, every for NVLink between CPU and GPU, between GPU to GPU, everything is now encrypted. And so it's confidential computing safe. This allows companies to feel safe that their models are being deployed by somebody else, but it will never be seen by anybody else. Okay? And so this particular system is not only incredibly energy efficient, and there's one other thing that's incredible. Because of the nature of the workload of AI, it spikes instantaneously with this computation layer called all-reduce. The amount of current, the amount of energy that is used simultaneously is really off the charts. Oftentimes, it'll spike up 25%. We now have power smoothing across the entire system so that you don't have to over-provision by 25 times, or if you over-provision by 25 times, you don't have to leave 25%, not 25 times, 25% of the energy squandered or unused. And so now you could fill up the entire power budget and you don't have to provision beyond that. And then the last thing, of course, is performance. So let's take a look at the performance of this. These are only charts that people who build AI supercomputers would love. It took every single one of these chips, complete redesign of every single one of the systems and rewriting the entire stack for us to make this possible. Basically, this is training the AI model, this first column. The faster you train AI models, the faster you can get the next frontier out to the world. This is your time to market. This is technology leadership. This is your pricing power. And so in the case of the green, this is essentially a 10 trillion parameter model. We scaled it up from DeepSeek. DeepSeek, that's why we call it DeepSeek++. Training a 10 trillion parameter model on 100 trillion tokens. Okay? And this is our simulation projection of what it would take for us to build the next frontier model. The next frontier model, Elon's already mentioned that the next version of Grok 5, I think is 7 trillion parameters. So this is 10. And in the green is Blackwell. And here, in the case of Rubin, notice the throughput is so much higher, and therefore it only takes 1/4 as many of these systems in order to train the model in the time that we gave it here, which is 1 month. Okay? And so time is the same for everybody. Now, how fast you can train that model and how large of a model you can train is how you're going to get to the frontier first. The second part is your factory throughput. Blackwell is green again, and factory throughput is important because your factory is, in the case of a gigawatt, is $50 billion. A $50 billion data center can only consume 1 gigawatt of power. And so if your performance, your throughput per watt is very good versus quite poor, that directly translates to your revenues. Your revenues of your data center is directly related to the second column. And in the case of Blackwell, it was about 10 times over Hopper. In the case of Rubin, it's going to be about 10 times higher again. Okay? And in the case of now the cost of the tokens, how cost effectively it is to generate the token, this is Rubin, about 1/10. Just as in the case of, So this is how we're going to get everybody to the next frontier, to push AI to the next level, and of course, to build these data centers energy efficiently and cost efficiently. So this is it. This is NVIDIA today. We mentioned that we build chips, but as you know, NVIDIA builds entire systems now, and AI is a full stack. We're reinventing AI across everything from chips to infrastructure to models to applications. And our job is to create the entire stack so that all of you could create incredible applications for the rest of the world. Thank you all for coming. Have a great CES. Now, before I let you guys go, there were a whole bunch of slides we had to leave on the cutting floor, and so we have some outtakes here. I think it'll be fun for you. Have a great CES, guys.
And cut.
NVIDIA Live at CES Take 4 Marker.
Boom mic. Action.
Sorry, guys.
Platform shift, huh?
大家好，我是主播周玉琴。很多的朋友告诉我们，太阳星全效克菲尔益生菌帮助了睡眠品质。原版的太阳星全效克菲尔益生菌，它添加有超级食物羽衣甘蓝，健康再加分。而有睡眠困扰的朋友们，赶快选择蓝色包装这一款晚安加强版，绝对是更有感。每日克菲尔，时刻美好 ，Good Feel Good。请上快点购为健康下单，而且要记得输入推荐代码，有额外的折扣优惠。太阳星全效克菲尔益生菌基础版、晚安加强版，新包装改版，内容不变，抽取更方便。要吃就吃最好的。